Bismillahirrahmanirrahim. In this lecture, we are going to speak about the definite integral. Starting with the definition, then evaluating the definite integral using Riemann sum. For the definite integral, we say that if f is a function defined over or for a less than or x less than or equal to b over this interval on a to b, then we divide the interval a to b into n sub-intervals of equal with b equal or delta x equal to b minus a divided by n. So we are partitioning the interval between a and b into n sub-intervals, where delta x equal to b minus a divided by n. And we need that the initial or the starting point x sub 0 equal to a and x sub n equal to b. Be the endpoint of these sub-intervals, and we let x1 star, x2 star, x sub n star be sample point. Sample point means we can choose any point in the interval, any point there between xi and xi plus 1. Then the definite integral of f from a to b is given by this symbol, which is well, a to b, because this is the integral symbol. F of x dx equal to the limit as n goes to infinity of the sigma f of xi star multiplied by delta x. But one condition that the limit exists. If the limit of the right-hand side exists, then the integral or the integration of the function equal to the limit as n goes to infinity of the summation. This will give the same value for all possible choices sample points. In this case, we say that f is integrable on AB. If the limit exists, then we say that the function is integrable over a and b. Integrable means we can find the value or finite value for this process integration. And to approximate the idea, if f of x is greater than 0, then this we call it Riemann sum. Sigma x or sigma f of x I star multiplied by delta x is Riemann sum, which can be represented by this figure. We are partitioning, creating rectangles for these subintervals, and add all of them together. This will estimate the area under the curve. For the integration, we are using continuous function for the symbol integration. Then if it is integrable, then the sum or the limit equal to the integration of the function. And to evaluate the definite integral in some functions, like what we have here in this figure, it can be positive or negative. So the definite integral a to b f of x equal to a1 minus a2. a1 means the positive when it is above the x-axis, and a2 is the negative value, or we can say a1 is the area of the region above the x-axis, and a2 is the area of the region below the x-axis and above the graph of the function. So let's think about this is a2 and this is a1. So the value of the definite integral is equal to the a1 or the area above the x-axis in the positive minus the area under the x-axis and above the graph or the curve of the given function. Sometimes we need to evaluate this function using the sigma or the Riemann sum. So we can say that if f is integrable on a, b, on the given interval a and b, then the integration of the definite integral or the value of the definite integral a to b f of x equal to the limit of the Riemann sum, where delta x equal to b minus a divided by n, and xi equal to a plus I times delta x. Now to evaluate this definite integral, we need to know some of the power series. These are the basic, first 4 basic series. Sigma of 1, as I go from 1 to n, is equal to n. We need this later on. Sigma of I is equal to n multiplied by n plus 1 divided by 2. Sigma of I square equal to n multiplied by n plus 1 times 2n plus 1 divided by 6. And sigma of I cube is equal to n times n plus 1 divided by 2 all to power 2. To apply this for the definite integral, try to evaluate sum of the definite integral using this power series. For example, number 1. Let's say example number 1. This is estimate or evaluate. The integration from 0 to 2 of 1 dx. This is a constant function. It is very easy to find the value for this one, but I'm going to use the Riemann sum to evaluate. Okay, let's say using Riemann sum. Now for this one, the first step we need to find delta x. Delta x, which is equal to b minus a divided by n. That's equal to 2 minus 0 divided by n is equal to 2 over n. And we know that the integration is equal to the limit as n goes to infinity of sigma I equal to n or 1 to n f of xi star times delta x. My function, this is my f of x. So this is equal to limit sigma 1 multiplied by delta x is given by 2 divided by n as I from 1 to n. And n goes to infinity. This is 2 over n. I will take it outside because I need to care just about I. Since I don't have I, this is constant. So this is equal to limit of 2n multiplied by sigma I equal to 1 to n of the constant 1. And as we stated before, sigma of 1 is equal to n. So we can replace sigma of 1 to be n. And so this is not 2n, this is 2 divided by n. So I will have limit of 2 divided by n multiplied by n. This is the value of sigma equal to n as n goes to infinity. You can simplify, take n with n. I will have only 2. So the limit of the constant is the constant itself. So it means that the value for this definite integral from 0 to 2 of the 1 dx is equal to 2. We just applied the limit for the Riemann sum as n goes to infinity, and we found the value of the definite integral. Let's have another example. Example number 2. For that, we need to find 0 to 1 of x dx. As we did, we'll find delta x first. So delta x is equal to 1 minus 0 over n, that will be 1 over n. And we know that x I is equal to a plus I delta x. Now, a is equal to 0 to the left end of the interval, or the lower limit of the definite integral. So xi can be written as I multiplied by, or take it 0 plus I multiplied by delta x, which is 1 over n. That will be I times 1 over n. This is xi. I need to replace it in the function later on. Now the definite integral 0 to 1 of x dx is equal to the limit of sigma I from 1 to n. My function is x, so it is xi in this case, times delta x. So it is f of xi, and my function is x, so I'm going to replace the function by xi or xi star. I can use xi or just xi star. As n goes to infinity. This is equal to limit as n goes to infinity multiplied by xi is equal to I multiplied by in, or 1 over n. So it is sigma 1 to n of I multiplied by 1 over n multiplied by delta x, which is 1 over n. So I will take 1 over n outside the sigma. So this is equal to limit as n goes to infinity of 1 over n square multiplied by sigma of I from 1 to n. And we know that the sigma of I is equal to n multiplied by n plus 1 divided by 2. So this is equal to limit of 1 over n square multiplied by value for the sigma is equal to n times n plus 1 divided by 2 as n goes to infinity, which is equal, just open the bracket and simplify it. One over n square multiplied by n square plus n divided by 2. And we know that for the limit at infinity, we are taking the highest power if we have rational function. So I'm going to have or take the highest power for the numerator and the denominator. So I'll have n square and 2 n square. Take the highest power for the numerator and denominator. And then simplify. N square will cancel n square. I will have only 1/2. So the limit will be 1/2. Means the definite integral from 0 to 1 x dx is equal to 1 over 2. So this is the idea of using the Riemann sum or the limit expression to evaluate the definite integral. Or what we need just to convert the definite integral into Riemann sum, replace any x in the function by xi, any x in the function, replace it by xi, this one. Then apply the limit, evaluate and simplify to find the value of the definite integral.